Okay, so this is the Bayesian section for week 7. I'm not even in the right directory. So this week we're talking more about Stan, and there's a zip file on Courseworks that you can unzip, and it'll have all the information for what we're going to be talking about today. So the first thing, you're going to need to install a couple additional packages, the energy package and also the LARS package. We'll have an example that we're going to go through toward the end. So the first thing that we want to do is to compare the performance and the efficiency for the same posterior distribution, which is just going to be a posterior distribution with improper priors on the coefficients, using a probit model to predict whether or not a baby is going to have low birth weight as a function of the characteristics of the mother. And so for any probit model, we can write the log likelihood like this: the sum of actually Bernoulli distributions with size equal 1. The probability is equal to the predictors times the coefficients, and we'll run that through the standard normal CDF to get probabilities on a 0-1 scale. We want to have the Bernoulli probabilities in log form. We sum over that. That gives us a log likelihood. We could add whatever priors we want, but in this case, I'll just do flat priors in all cases to keep these comparable. So there's an example in MCMC Pack with this low birth weight data set. First, we can create the Y and the X that go along when predicting low birth weight as a function of the age of the mother at the time of the birth, the mother's race, and whether the mother was smoking during pregnancy. So the first example, if you remember back a couple weeks ago, I presented what I called a universal Gibbs sample, but I actually said a Gibbs sampler, but I actually said not to use it. And today we get a more clear indication of why you shouldn't use this, although it's conceptually valid. So this is just the thing we saw a couple weeks ago, where you loop over the iterations, you loop over all the variables, you use the PM new to create an approximation to the full conditional distribution for the coefficient, and you draw once from that inverse CDF approximation, use that as your draw for whatever the case parameter is, and just go around and around. And so it's good to choose good starting values. In simple models like this, you might want to start it at the maximum likelihood estimates, and you can obtain maximum likelihood estimates of a probit model using the GLM function, specifying the family, which is basically a weird word for likelihood, is binomial or a special case of binomial Bernoulli, with link function probit. So link function, again, refers to the transformation of the linear predictor to the space of probabilities, in this case for a discrete and more specifically binary variable. We're using the standard normal as a link function here. The canonical link in statistics, at least, is the logistic link function, otherwise shorthand known as a logit model, where we would use p logis for the link function here rather than p norm. But it should be clear that any CDF from all real numbers that has a sample space of all real numbers would be a candidate for a link function in a binary model. It's just the logistic one has some properties that make it easy to do maximum likelihood, but the probit is really no harder. And so our Uneron is very slow. So this took me like 2 hours to do this morning. So rather than you executing that code, although it's legal code and it does run, what I'm going to do is load a copy that I did this morning. And these are the things I was not able to get onto Courseworks yet because of the size requirements in Courseworks and because I probably ran too many iterations. But anyway, I did that this morning. And if it was not so bad, we could look at it. The next, and we will look at a plot of it in a second. So the next, the second of the 4 ways to do a probit model is to use a Metropolis Hastings sampler. Now, we already saw that there's an MCMC probit model already in MCMC Pack, and you should actually use that if you wanted to estimate a plain probit model. But if you wanted to estimate an arbitrary model, sort of in the R Uniron sense, there is a generic random walk Metropolis Hastings sampler in MCMC Pack, whose name is MCMC Metrop 1R. And the arguments to that function, did I not? I already loaded in. So args are the function, the kernel of the posterior distribution, starting values, a bunch of other stuff. One thing to keep in mind when doing MCMC Pack stuff in parallel is if you don't choose a seed, it will use the same seed for all of your chains, in this case, 8 of them. So you have to choose a non-default value for that. I'm just sampling a random integer, doing that on the R side and passing that as a seed. So this actually runs fast enough to contemplate doing. Do I have my parallel library open? Hopefully I did. So this did not go well. What happened? Oh, forgot to paste in the stuff from above.
MC course doesn't work on Windows, apparently.
MCLapply will not go in parallel on Windows. It should execute the code just serially. But in any event, you don't actually need to do this, but it doesn't take terribly long. And this one we can look at using the summary functions of CODA. In any event, we get estimate for, negative, in this case, for the mother's age. I'm not sure what 2 and 3 refer to as the race categories, but I guess the point of this was that if the mother smoked during pregnancy, then you have a positive and more or less precisely estimated distribution that has a positive coefficient indicating an increased probability that the baby would have low birth weight. And here we can see the median and the other quantiles that go along with that. So that's Metropolis Hastings' approach to the probit model. Then there is Stan, of course. And so let's look at the Stan file, which I hope I put in that zip thing.
You did.
Yes.
Good. Okay. So again, Stan programs may be extremely complicated, but they certainly don't have to be. So for data, we're declaring the number of observations N, the number of predictors K, the N by K predictor matrix X. And in this case, because the Y data are integers, 0 or 1, we are going to declare an integer array with a lower bound of 0, an upper bound of 1. These lower and upper bounds, if I didn't say them before, are interpreted inclusively. So
Meaning what?
zeros and ones are consistent with that restriction. So they're not the exclusive intervals. But because, so ordinarily you might think of this as a vector, a binary vector, but vector in Stan means real numbers, and you can't pass vector of real numbers to the Bernoulli likelihood in Stan. So we have to declare this as an array of integers of length n. In any event, that's how you handle discrete outcomes. So we just have one set of parameters beta. Those are the coefficients in our probit model. And in order to do the likelihood, it's easiest to do it in a couple steps. We're going to declare local variables that are vectors of length n, eta, and p. These two are not going to be stored in our output because we declare them inside the model block. If these had been important enough to worry about, I would have put them in a transformed parameters block, but they're just deterministically related to the parameters. So if I really wanted them, I could recreate this in R, but they're not particularly special. Eta is just the linear predictor, x multiplied by the vector beta. And then for each of the observations, I'm going to go through and call the phi function, which is for the standard normal CDF on the linear predictor for the nth observation, and stick that into the nth element of the vector p. So p will all its elements be between 0 and 1, and then I pass that whole p vector as the argument to the Bernoulli likelihood function for y, and I'm done. What you'll see a lot of times, and I've said that this is not very smart, is you'll see something like this, or maybe they'll just declare p to be a scalar or whatever. So this is a bad idea. Because it requires Stan to allocate memory to figure out the derivatives things n times. Whereas if you do it the way we did it before, which is the correct way, and pass the whole vector of p's and the whole array of y's to the Bernoulli function at once, it only has to allocate memory once to handle all those derivatives, because the derivative of a sum is the sum of derivatives. And so when it's figuring out the derivatives of this likelihood function with respect to beta, it just needs to allocate enough memory to do that once, and then it can keep summing to that thing as it's evaluating the Bernoulli likelihood. So this also goes pretty quick. Again, the quickish. The default in Stan is for only 4 chains, and I think that's a bit unfortunate. 4 is kind of too small to do some of the things that I like to do with diagnosing the results. So I usually do at least 8, but even more would be better. So this doesn't take too long.
So with the chains, I remember just kind of using the missing data class, the benchmark here. Some people use 5, imputations, some use 10. What's the benchmark you use to know whether you've done enough chains?
Right. So in this case, there's 2 things, 2-ish things to keep separate. So one is how many draws do I need to get effective inference? And that is going to be driven by effective sample size that we talked about on Tuesday, Thursday. It's definitely this week sometime. We talked about the effective sample size. So you know the nominal sample size whenever you go in, but you don't know the effective sample size until you do it. But certainly if you're interested in estimating a mean, then an effective sample size of like 100 is probably going to be give you adequate precision if everything else is going well. So whether you do a small number of chains and kind of a bigger number of iterations in order to get a given effective sample size, or a larger number of chains and a smaller number of iterations to get an effective sample size, technically speaking, that doesn't matter a whole lot. But there's an additional consideration on top of that, which is how many chains do I need in order to do an effective diagnosis of whether the chains went well. And that is what I'm saying. 4 is kind of too small, even though it's adequate for inference, presuming everything goes well. It's not so adequate for diagnosing whether everything has gone well. And we'll get to this later on, but what we talked about on Thursday, this idea of within chain and between chain distances, basically in order to estimate the between chain part of that with enough precision, you need a not 4 number of chains. So the distances among the chains are, there's chains, choose 2 of them. So 8 would be 8 times 7 divided by 2, or 28. And that's, probably enough. But 4 choose 2 is just 6. So that doesn't really enable us to estimate the between components of some of these things terribly well. So I do multiples of 8 because this computer has 8 cores and it can do those simultaneously. But I think 8 is probably a good minimum number to do the diagnostics that we want to talk about today. And that's probably more than enough to give you, if everything goes well, an effective sample size that's large enough for you to compute the expectations of whatever it is you're interested in. But you have to do more chains than you really need in order to diagnose the chains. You have to do more warm up than you really need in order to let Stan do its adaptation thing. So there's additional considerations that sort of point to using more resources in order to really do the whole thing effectively, even if that is kind of overkill for doing the analysis substantively.
Can I ask 2 questions on the probit Stan file, the other code?
Yeah.
Maybe they're stupid, but so I think you explained why the why Bernoulli is not in a loop, but why do we need the loop in the line before? Like, can we not do this?
So some Stan functions will accept a vector and spit out a vector, and some don't. Okay. For whatever reason, it usually just prioritizing effort. The standard normal CDF does not take a vector and output a vector like it would in R. It takes a scalar, outputs a scalar. But these loops, unlike in R, doing a loop is not really slow. Basically, when this gets translated to C++, it would be the same process, same number of flops and all that. In R, it's slow because function calls are slow, but in a compiled language, that doesn't matter so much. What you don't want to do, if possible, is to put a likelihood or a prior inside a loop, because it has to do memory allocations for every iteration of the loop. And that's actually what's slow, not the function calls or even figuring out what this area is. It's the memory allocation and then destruction.
Okay.
So the second question.
Why do we omit the priors, and what does it do if we omit? Is it just for now, or? Yeah.
I wanted these 4 ways of doing the probit model to be comparable. And the Gibbs sampler that we're gonna do next, it gives limited choices for what the prior could be. It yields a proper posterior. So this is not wrong, but if you had prior information or even weakly informative priors, you could probably get a more precise posterior distribution if you cared about the effect of smoking on low birth weight children. Dan?
Just curious, when you say something, so if we do the sum of the residuals, I guess we do the residual sums instead of the sum of the residuals. How much does it actually slow it down? Because at this point, I'm just worried about functioning in Stan's language, and I'm sure that I'm not going. Are we talking about twice as long? 3 times as long?
It can be multiple times as long. It particularly depends on how many observations you're dealing with.
Right.
So
And how many coefficients are?
More
More observations.
on the observations. So it does depend on the number of coefficients as well, but that's not so much the dominant thing. So in this case, when I'm doing the likelihood correctly, then the number of coefficients is relevant because the likelihood is actually executed pretty fast. But if I was doing it the wrong way, then the slowdown would be dominated by the likelihood. Basically, the slowest thing in Stan is putting the derivatives in the right places for it to then do the chain rule over. So you want to minimize the number of times that it has to put derivatives in its memory in the right places that it can then sweep over. So, but it's easier to do it the right way this way than it is to do it the wrong way. But bugs, which is what a lot of people who use before they use Stan, they would use bugs. You had to do the loop thing. It didn't have so much about vectors. And so you'll see a lot of Stan code that has been sort of literally translated from bugs where they don't, go through and actually do it the right way. So they get something and then it runs slow and then they complain. And then we tell them you have to write the likelihood correctly. Anyway, the fourth way of doing a probit model is with the Gibbs sampler that we talked about a couple of weeks ago. If you introduce this latent utility variable, then the full conditional distributions of the coefficients have a known form, happens to be multivariate normal, and the full conditional distribution of the latent utility is truncated univariate normal. Both of those are easy to draw from, and that overcomes sort of the fundamental limitation of a Gibbs sampler, which is that the full conditional variance can be much smaller than the marginal variance when the parameters are highly correlated. But if you can update potentially highly correlated parameters in one bunch, so all k coefficients together with some k by k covariance matrix that goes into that multivariate normal full conditional distribution, then you no longer have that problem. And so this is sort of the best example of a Gibbs sampler with data augmentation working really well and that quickly. So if we then want to do a comparison of these approaches using the dependence plot that I talked about, and now I have in the wrong folder. Let's that in. Also, my other one. Okay, so if we want to compare the dependence plots that I was putting up yesterday to see which of these approaches is the most efficient, we can go like this. You don't have this file?
No, we don't have running around.
Oh, yeah, it was too big. In any event, trust me, if you had the files to make it, it would look like this. Or you could make one just with the bottom two. Let's see what happens if I pop this out. Shut up.
We ran MH as well, right? So
Yeah.
we can get the bottom 3.
Always allow pop-ups. Yes. Okay, try again. Okay, looking better. So the top left one is for the R Unaron thing that I said to not use. And you can see for one lag, the dependence is about 0.7 as estimated by the distance correlation. And then it kind of slowly gets lower after that. So 3, 5, 7, but even to 13 lags back, it's still nowhere real close to zero distance correlation, and zero distance correlation characterizes independence. So the draw now is not independent of the draw 13 times in the future or 13 times in the past. You know, maybe it did if we ran the lag length out to 25 or so. But in any event, it's has relatively high dependence among the parameters, even though this is an extremely simple model by any standard. And that means the variance inflation factor in our estimated means is going to be higher when it does the sort of infinite sum over the parallelogram. The amount of time it's going to take to get from wherever it starts to convergent distribution to the posterior distribution is going to take longer, etc. So if you only had our Uneron, you could probably make it work eventually, but there's no reason why you should really feel limited to that approach. The one in the top right is for the Metropolis Hastings, which was basically a kind of a better version. It's not using Gibbs sampler, but it's a better way than the Uneron thing to sample from some arbitrary posterior distribution that you can just write down as a R function and sample from. So in this case, it looks, it starts out about, again, 0.8 distance correlation among consecutive draws, but it falls off a little bit faster, such that by the time you get, somewhere between 12 and 15 lags, the draws are essentially independent of each other. And then you could do a test of the null hypothesis that all 8 chains have the same distribution if you thin them by the appropriate amount there. In the bottom row, it's even better. So the bottom left, we have Stan, which again is comparable to Metropolis Hastings in the sense you can write down an arbitrary posterior distribution and sample from it. The difference is for Stan, you have to write it down as a Stan file. Metropolis Hastings, you could actually just do an arbitrary function in R. But that's kind of a small additional hurdle to get over, considering how much better performance the sampling is. So for, after it gets, all the chains to the posterior distribution, which looks as if it happens around here, oftentimes in Stan, you'll see the dependence fall precipitously toward the beginning of the warm-up period. So when the chains start off, they're starting off in different places, and they don't have the same distribution. So it's reasonable to expect their between chain distance when they start is bigger than the between chain distance that they're going to have when they get to the same posterior distribution. So these ratios of B over W that we're talking about are basically inflated in the period when it hasn't gotten to the posterior distribution yet. Consequently, the dependence among consecutive, or not even consecutive, but nearby draws tends to be larger when the chains have not gotten to the posterior distribution yet. But this, we see a pretty typical pattern where the dependence gets low and then it gets pretty constant. Of course, for a lag of 1, by definition with a Markov chain, there's not going to be zero dependence in that. But really by 2, or, it kind of, the 2 one pokes up a little bit a couple times, but 3 or 4, it definitely gets near 0 and stays near 0. So that's looking like it's doing pretty good. Again, you can see rug marks in the warm-up period indicating that one of the chains had a Hamiltonian divergence for these iterations, but you don't see any of that in the post warm-up period. So that's another indication that things are going well. And then in the bottom right, you see MCMC Probit with the Gibbs sampler and data augmentation and the latent utility. And it's basically getting the same performance as Stan. The MCMC pack doesn't keep the burn-in iterations. So this 0 is actually comparable to 1,000 in Stan. So this doesn't show as it's getting to its posterior distribution. But basically the red line and the green line and the blue lines are about the same. And so this, I think, is pretty optimistic for Stan because the Gibbs sampler with augmentation of these latent utility things is one of the best performing Gibbs samplers that there is, because it can update all the parameters, because the only parameters are the coefficients aside from the latent variables thing. It can update them all at once. Most Gibbs samplers, it has to update the coefficients and then it has to update the variance, and there might be other parameters if we're doing a hierarchical model. And in that situation, we get into things where the marginal variance is a lot, the full conditional variance is a lot smaller than the marginal variance, and it's not jumping very far. It's just making tiny jumps that get a lot worse dependence and a lot more time to reach the posterior distribution. But certainly in this case, it's performing really well, and the dependence dissipates really quickly. But I'm saying that this is kind of the best case for a Gibbs sampler, and this one is known to converge to the posterior distribution at a geometric rate, which is basically the fastest possible for like non-toy models. But this Gibbs sampler with data augmentation comes with the limitation that you can't really change very much about it. You're allowed to choose any prior over the coefficients in the multivariate normal family. But if you didn't want to put a multivariate normal prior on the coefficients, you could write down a valid posterior distribution, but you would not have a Gibbs sampler anymore. So you couldn't do, any of the non-informative priors that we talked about this week that are kind of special. If you change it from a probit likelihood to a logit likelihood or some other likelihood for a binary response, you no longer have a Gibbs sampler, etc. So this is good performance for a Gibbs sampler, but it's not going to generalize much beyond this particular situation. Jasper.
So just just to clarify, the rug plot on the Stan x-axis is telling us, is it the number of leapfrog steps, or is it like the extent to which the draw of theta like diverges from the previous theta given
So it means for this iteration, 498 or something like that, at least one of the chains, the leapfrogger, exceeded its theoretical upper bound, indicating the leapfrogging must have gotten inaccurate relative to the true Hamiltonian, and it stopped the leapfrogging without getting to the U-turn point. So when that happens, particularly if it happens after the warm-up period, that's suggesting that the chain, that it's having a hard time moving accurately and getting the good proposals that are relatively far from the current draw, but still are going to get accepted with high probability, etc. That really makes nuts work well. But you will oftentimes see divergence during the warm-up period where it's trying to figure out the epsilon and it's trying to figure out the m, and it's maybe not even exactly to the posterior distribution yet. So its preliminary guess of what a good epsilon and m will be has to get revised later and before it gets frozen when the warm-up period starts. And so this is why I would say this is optimistic for Stan also, because it achieves the same performance essentially as the Gibbs sampler in the best case for a Gibbs sampler, But a Stan program is comparable to what you can feed to Metropolis Hastings. You just have to accumulate up an arbitrary posterior kernel. You can use whatever priors you want, can change the likelihood however you want, and there's no latent utility or anything like that is a trick going on here. So you could be optimistic that you would get the same sort of performance if instead you were using a logit likelihood, or if instead you were using a slightly different prior than multivariate normal. So these two or actually all three of these are general in the sense that you can get an arbitrary posterior kernel. The R Uneron is just not appropriate for MCMC because it has so much dependence and is so slow. Metropolis Hastings has more dependence than nuts, but they're sort of equally fast. And so that's why it's preferable to use nuts over Metropolis Hastings. But if you can get the same performance as the best Gibbs samplers, then you don't need to worry so much about learning the ins and outs and the tricks and whatnot that go into getting good performance with Gibbs sampling. If you can get the same good performance with Stan for no sort of restrictions on the generality of the things that you can do. Abit?
Yeah, sorry, I think I might have missed this, but the Gibbs sampler plot isn't showing the warm-up period.
Right. That doesn't get retained. Yeah. So there would be, if it showed the burn-in period, there would be a little landing like we got over here. Dane?
So this is just a basic question about the data that each of these functions spit out. So on the R Uneron and the Metropolis Hastings, how is it differentiating between the lag lengths? Did it run different?
No. So it just got like 2,000 draws for all four of these, and then 8 chains for each of these 4 ways of doing it.
Right.
And so at, let's say, iteration 1250, there's 8 draws from the posterior distribution. And at iteration 1257, there are 8 draws ostensibly from the posterior distribution. And it calculates the distance correlation at those 2 points. And that would be reflected by the light blue line. It estimated a distance correlation, and this has some smoothing to it.
So it's using the same chains and then just
different parts of them.
Yeah. Okay.
And then going all the way across, and I can do that for different lag lengths on the same data or same draws from the posterior distribution.
And so you said, I think in the lecture, it does include the dependence between for example, one parameter at point T and another parameter and another element of the parameter vector at the future.
Yes.
Yeah.
So the distance correlation is based on the joint distributions at those 2 time points, and the number of columns by default, and in this case it would hold, is the number of parameters in your posterior distribution. So 5 or something in this case. But anyway, it's doing the same calculation on all of these, and all of these represent the same posterior distribution, just different algorithms to draw from them. And, the ones on the bottom are clearly doing better than the ones on the top.
And so again, when it's doing the leapfrog in Stan, so we have the lag length that we can measure it at 1 here.
Yeah.
If we had a leapfrog that was larger, could we not measure those smaller lag lengths?
So there's going to be multiple leapfrog steps in every iteration. It's actually going to be 2 to the tree depth leapfrog steps in each iteration. So we don't actually.
The size of those steps, does that matter for?
Yeah, it does. We'll look at one of the step size things. Basically, in order to get this like really good performance, and this is about as good as it gets, you need to have a step size that is as big as you can get away with without getting inaccuracy relative to the true Hamiltonian. So if you're taking big steps, you're more likely to hit the U-turn point before something bad happens. And basically, if you're getting to the U-turn point, then Stan should work pretty well. The Gibbs sampler doesn't have a U-turn point, but it was also getting pretty big jumps because it could update all K parameters at once without falling into some unlikely part of the posterior distribution.
That was actually very helpful, but I'm still, what's the relationship between lag length and the leap length there? Is that none?
Yeah. So this is lag length for iterations. So the difference between,
so it doesn't matter how big a gap there is between the iterations.
Right.
It's just measuring.
So yeah, leapfrogging is an intra iteration concept. It has to do a whole lot of leapfrog steps to make a proposal to then decide whether to accept or reject.
Right. Okay.
And once it decides whether to accept or reject, that is an iteration. And we're looking here at the dependence between closely in time separated iterations. And leapfrogging is only applicable to Stan anyway. So Stan got good performance here. So did Gibbs sampling. Stan would hopefully generalize that good performance more than Gibbs sampling would. And so if we want to test the null hypothesis that all the 8 chains have the same distribution, we can do this convergence test thing. Oh, I forgot this part. So once you sort of get an idea of some lag length that you think might get the dependence to be 0 consistently through the whole post warm-up period, you want to look at in more detail for a particular lag. So if I scoot this over, we have the plots with just looking at a lag of 4. And in this case, we can get 95% confidence intervals for the distance correlation, assuming the distance correlation to be 0. And it does, look, the smooth line definitely looks as if it's, staying near 0 in both situations when you go out 4 lags. But moreover, there's just a handful, and you probably can't even see them on the screen, but like that's one that exceeded its 95% confidence interval. But it doesn't look as if, more than 5% of the estimated distance correlations are outside the 95% confidence interval. So this looks as if it might be 4 might be a good number of lags to thin with when doing the test of the null hypothesis that all the chains have the same distribution. And you can see the results of that here if you call the convergence test. Remember, I said it's actually doing something comparable to a 2-way ANOVA decomposition of the energy distances. We have a contribution to the total distance for each chain. We have a contribution from the total distance for each split. So it pools all 8 chains together in the first 500 iterations past the start, past the end of warm up, and then the second 500. So there's a contribution, that and the interaction of the chain and the split. So there would actually be 16 half chains in this situation. And we can test the null hypothesis that each of those, after thinning, basically the expected distance within a group is equal to the expected distance across groups. And that would be consistent with the chains all having the same distribution. You can see here we get ratios of the between to within that, might be a little bit less than 1, might be a little bit bigger than 1. But in any event, we have p-values for the null hypothesis that all the chains have the same distribution. In this case, all the p-values are not small. So we would fail to reject the null hypothesis that the chains have the same distribution for Stan. And also if we do it for the Gibbs sampler, come on, Gibbs sampler. Again, pretty much the same thing. And we know in this case, it's a narrow but result that we can prove that the Gibbs sampler in this case is actually going to be converging to the posterior distribution at a geometric rate, which basically means the number of iterations is in the exponent of a thing that's between 0 and 1. So that is going to converge very quickly. And, the evidence we see here is consistent with that. So questions about what we were doing with that? No? Okay. So that is a comparison of basically the same posterior distribution with different algorithms. Now we want to compare the performance of Stan for different parameterizations of what conceptually is the same posterior distribution. So there's a prior that has become popular in certain subfields called the horseshoe prior. It's a prior for like regression coefficients. And it says that the conditional distribution of the conditional prior distribution of the regression coefficient is normal with mean 0 and standard deviation lambda for each of your regression coefficients. And then furthermore, lambda is distributed what's known as half Cauchy. So the absolute value of a Cauchy random variable with median 0 and scale tau. And tau in turn is also distributed half Cauchy with median 0 and scale 1. So this is an example of a hierarchical prior. And
does it look like a horseshoe? Is that way?
Not the prior.
I'm trying to layer this.
The posterior distribution, in a manner of speaking, can. But I will show you what the marginal prior looks like. So we can draw from this in R independently pretty easily. We'll just do 1,000 draws here. We'll draw tau. We'll take the absolute value of it from a Cauchy distribution. Then we'll draw lambda with a scale of tau, again, taking the absolute value. And then we'll draw normals for the betas with a standard deviation of lambda.
Sorry.
Yeah, go ahead, Anna.
No, I was just wondering, so how do people come up with these particular priors? Or why?
I could send you a link. There's a lot of math behind them. The intuition is people, and this is often used as a prior by people who are doing regression models with genetic things, is, well, I'll show you the shape of it as I'm answering the question. So where is it?
After you get enough, people just stop asking questions about your research and they just assume.
I'm in 4 mode. All right. So the marginal distribution of beta looks like this. Except you can't see it there. It looks like this on my screen. Right. So what they want, what they said they wanted was a prior distribution that was extremely concentrated near 0, but had extraordinarily long tails. So there was some prior probability of observing a regression coefficient that was very large. So this actually runs out to in the thousands, but I chopped it off after some point. So the genetics people, they have more predictors than they have observations because it's very expensive to get someone's DNA and something like that. But once you have it, you have millions of, chromosomes or something that could predict susceptibility to some hereditary disease. And they go in with the prior information. I think most of my coefficients are going to be near 0, but I'm hoping that there are some that really pop out as being big, and then they know to do experiments, trying to find people that only differ on that chromosome or whatever. So their prior, it's not even a prior belief, it's a prior bet that they can throw in like a million predictors, and 99% of them will be negligibly different from zero, and substantively they don't have to worry about those, but some of them are going to have a coefficient of like 300, and they want to find out what those are.
It's naturally horseshoe.
The horseshoe refers to the posterior distribution of some things, not the prior. Anyway, so backing up a little bit, we got a distribution. So this is an example of dependence without correlation. So if we want to ask ourselves, what is the correlation between tau and beta? By construction, there is none, because lambda is a function of tau, and lambda is just the standard deviation on this normal prior. So there's not going to be any linear dependence, although this is because of the massive tails. It's an extremely noisy estimated correlation. But even though by construction there's no correlation in the population, there is dependence, and that can be quantified using the functions in the energy package. Maria Rizzo, who wrote the paper that we were talking about yesterday, has this R package called energy that implements a lot of these ideas, inclusive of a test for independence of tau and beta, which is sort of a ridiculous test because by construction, beta has to be related to tau through the variance, but it isn't with plain Pearson correlation. But there's an extremely strong distance correlation between tau and beta, and that's because distance correlation is really a measure of dependence, and I kind of wish they hadn't put correlation into the name, because it's really something that's kind of different from linear dependence. In any event, tau and beta are highly dependent in the sense that when you get a large tau, you're going to be more likely to get one of these extreme values of beta. When you have a small tau, you're more likely to get a value of beta near zero. So rolling along, we got that. Oh, I wanted to compare this to a standard normal distribution. So you guys know the standard normal pretty well, but it obviously has a much narrower, effective range, and not nearly the peak at zero. And so if you're doing one of these genetic regressions, these standard normal priors are not nearly informative enough. So you could get a posterior distribution where genes have, or chromosomes have some non-zero coefficient, and then, you investigate it more closely, and it turns out that thing, didn't matter at all. You were basically just, that was something that you found when you went, data fishing. But ostensibly, if you put a strong enough prior, then, data mining is maybe not as much of a concern if you're sort of reflecting a strong prior belief that most of these are going to be zero.
How come there's so much more mass under the horseshoe than there is under the standard normal?
There isn't. They both have an area of 1 underneath.
The standard normal is just going up a lot higher than it looks.
Well, it's the pixels of this are messed up by the scale, but these are both probability distributions, and they both integrate to 1. But it's harder to see. In any event, so if we can do this textbook horseshoe thing in Stan relatively easily, once I get into the right directory again, week 7. Horseshoe textbook stamp. Okay. So this is just basically a regression setup in K, X, and Y. We'll have an intercept that's not subject to this horseshoe prior, because you wouldn't really expect the intercept to be so close to 0 if Y has a non-zero mean. The beta coefficient vectors, for each beta, there's a standard deviation lambda. The standard deviations lambda have a common scale, and then you have an error variance for the regression. So this, by not putting priors on the intercept and sigma, are equivalent or tantamount to putting flat priors over their respective sample spaces. In this case, we're going to put a Cauchy prior on tau. Now, this may look a little bit suspicious because tau is restricted to be non-negative, and the Cauchy distribution is over the entire real line. And so this technically is wrong in the sense the prior distributions you do should integrate to 1 over the respective sample spaces. However, in this case, the amount of prior mass that is excluded, which is to say the amount of mass to the right of 0 under the Cauchy distribution, is exactly 0.5, and the amount to the left is 0.5. So if we were to do the correct thing, which would be a truncated Cauchy distribution at 0, it would be dividing by 1 minus 0.5 in order to make the positive part of the Cauchy distribution integrate to 1 again. So it would be just dividing by 0.5, and if we subtract the logarithm of 0.5, that would just be a constant and would have no effect on what proposals get accepted and what get rejected. So it's wrong, but it's wrong by a constant. And if it's wrong by a constant, it doesn't matter. Jasper, you had a question about
I
that?
think this actually answers my question from before. When you were saying that the half Cauchy had a median of 0, we mean like
The real
distribution that's a
Cauchy.
half of
Yeah.
as a median. Okay.
Right. So the median of the half Cauchy is actually 1, I think.
Right.
But it has that huge
Okay, got it.
tail. So in this case, we don't need to truncate. If these hyperparameters were unknown, then the amount of mass being truncated is a random variable, and then it would be wrong by a non-constant if you didn't do the truncation, but you can do the truncation instead by just putting t and then in brackets the truncation point, lower and upper. But in this case, we don't actually need to do that. Similarly with the lambdas, those have a scale of tau, have Cauchy, and then, so that's wrong. The betas have a standard deviation of lambda, and then it all just goes into a regression function deal. So again, that takes a long time to do. So we'll just load up one that I already created. And if we do a dependence plot for this, takes a little while. So if anybody has a question, there we go. No more questions. So it looks like this, where here we're seeing Stan have, R Uneron like performance. Here we're taking lags out to 50, and we're still not consistently getting the dependence to get to 0 and stay to 0. And we see at least one of the chains having Hamiltonian divergence at basically every iteration. So this is an example of a perfectly valid posterior distribution that, with the sort of basic parameterization, Stan can't sample from that posterior distribution very well. And, this was a prior distribution, but it sort of conveys the same thing. When the first derivatives of the posterior distribution, the gradient, are themselves changing so rapidly that an approximation based on the first derivatives is only going to be accurate if you take extremely small steps. But because we've got these huge tails, if you took extremely small steps out in the tail, it would take forever to go anywhere. So Stan, it's only got the one epsilon that it can really manipulate. It tries to, split the difference kind of, and it ends up with an epsilon that's too big when the posterior distribution is near its mode, and then too small to be fast out there. And so basically, one way or another, it's going to wind up in Hamiltonian divergence almost always, because it can't do an accurate leapfrogging approximation to the true Hamiltonian thing for this posterior. And so one solution to that, we're going to skip all that, is to use a reparameterization. So, horseshoe, we have tap completion in this thing. Reparameterization. So this is going to involve putting standard normal priors on some things and doing transformations to imply the same prior information on the parameters of interest, in this case mostly beta and also a little bit lambda. So what I'm doing here is putting a standard normal prior on what I will declare in parameters as beta z, and in transform parameters I'll make the transformation that beta z relates to beta, in the sense beta is defined as beta z multiplied by lambda multiplied by tau. I've actually slightly changed the definition of lambda here, but in any event, this just relies on the property that if you have something that's a priori standard normal and you multiply it by some positive number, then the transformed thing is going to be distributed normal with standard deviation equal to the thing you multiplied it by. That property of the normal distribution that we have talked a lot about before. Also, so this symbol here with the dot star, that indicates element-wise multiplication rather than vector multiplication in the Stans index. I'm also going to put a standard normal prior on what I call lambda z and relate lambda to lambda z using the inverse CDF of the, in this case, half Cauchy distribution, but it's the same as the Cauchy distribution, where I'm going to put a priori lambda z is distributed standard normal. I'm going to run that through the standard normal CDF so that this thing is distributed standard uniform. And then I'm going to take that standard uniform thing, run it through the inverse CDF of the Cauchy distribution to imply that lambda is distributed half Cauchy, consistent with this horseshoe prior business. To do that, I wrote myself a function in the function block that I got this formula for the inverse CDF of the Cauchy distribution off of Wikipedia. So it's a tangent of pi times p minus 1/2, and that tangent is, has this basically huge tails thing, which drives the whole process here. So that is that. And if I do that in R, I need to load, what do I call this? Reparam. Now, so that was the dependence plot that we got for the literal horseshoe prior parameterization. And here is the dependence plot that we get for the reparameterization of the horseshoe in terms of what we call matrix on the normal distribution and inverse CDF transformations on these Cauchys. And here it's just extremely apparent that it's
You see the important part.
not to you, but it is to me and everyone watching on YouTube, that it rapidly or precipitously or something gets much lower dependence until it gets about here. It all flattens out, and we see basically, very negligible dependence. And this is one is red is 1 and 2 is green. Green is 2 and light blue is 3 and dark blue is 4. You can't see my legend. I should have put it on the other side. But in any event, so no longer the case that it takes 50 lags to not get to zero dependence. We get basically to zero dependence pretty fast, and without changing the logic of our posterior distribution at all. But yes,
Can I ask a quick
question?
But we still observe a lot of divergence. On
Yes.
The second step. So
And that is what I was going to talk about next. So if so, this is also going to look pretty good if I, go out to a lag of 8. Even 4 or 2 maybe, might have looked good. But when I do the test, where's my test? Even thinning to 8 intervals, I get the minimum possible p-value for 200 permutations. And you're like, well, what's going on here? And the reality of it, even though this is a lot better, the chains are still not having the same distribution because none of the chains are good at exploring the tails of this posterior distribution. And that is tied up with the fact we're still seeing a lot of divergence in the post-warm-up period, where basically it got unglued from its true Hamiltonian and was spewing out proposals that were not really theoretically in the right place. And, those sometimes get accepted, sometimes they don't. And chains had different degrees to which they are being afflicted by this. And consequently, the tails of our 8 chains are really not totally the same, even though probably in this case, the medians of the chains are going to maybe be pretty similar. And you can, Dane?
It looks like, and it seemed like we saw this on some of the earlier plots, that there's right at the end of the warm-up period, we see less divergence right away. And I don't, it seems like it's just a continuation, right? Why would we see
it freezes its epsilon and its m when it changes over from warm-up to post-warm-up. And so, yeah, you can see some changes around there. But this is basically indicating that it's confused as to what epsilon it should be using. So there's a pair, Jesper?
So sorry to go over this again, but I feel like I'm not understanding something that's really crucial here, which is why you're running the PDFs through the CDFs and why that helps.
Yeah. Okay. So to go back to that, that's the wrong one. To go back to here. So Stan is most optimized to have minimal leapfrogging and accuracy when it's dealing with normal distribution. So there's a lot of ways for the reason why that's true, but maybe the simplest ones to understand is the momentum is coming in from a multivariate normal distribution, and that's pushing the proposals. And so if the posterior distribution is also in the normal family, then this leapfrogging pushing business gets it very close to where it's truly supposed to be according to Hamiltonian. So anytime you can get a posterior distribution that's, independent normals, Stan is going to be able to deal with that really well. Now, you can't really fully control your posterior distributions because they also depend on the data. But what you can do when possible is to specify standard normal prior distributions, independent standard normal prior distributions on primitives, and do some transformations of those primitives into the substantively interesting parameters in ways that imply the same prior distribution that you would have put directly on the substantive parameters in what I call the textbook implementation of the horseshoe prior. So this is what we call mat tricking, where you have a standard normal distribution that you scale up by an unknown random variable, and then beta has this conditional normal prior with scale lambda. And this business results from the theorem that we talked about, where if you put a standard uniform into any inverse CDF, what comes out has the distribution of that for that inverse CDF.
Yeah.
So to make that work in terms of normals, we have to take something that's distributed a priori standard normal, put it into the standard normal CDF. That intermediate thing is going to be distributed standard uniform. We transform a standard uniform to anything that has a closed form inverse CDF inclusive of Cauchy, and the fact that it's half Cauchy doesn't make a difference here because I've restricted my lambda z's to be non-negative, so all these p's are going to be greater than 0.05 or 0.5, and consequently it's going to come out positive when it's run through this. But that, yes.
Sorry, just to clarify, so the reason we don't just draw directly from a standard normal is what you started with, right? Like basically this question of momentums, and the fact that standards prefers to have things standard normal first and then standard uniform later, basically transformed.
Those are the best things from Stan's perspective, and if you can do a transformation that simultaneously makes things the best from Stan's perspective without changing your substantive priors in your parameterization, then do so. And then, assuming this came out a little bit better, then just look at your posterior distribution of beta and just ignore all this beta z and lambda z primitives. We're just drawing from their joint posterior distribution and basically integrating them out by ignoring them. And then we get a marginal posterior distribution of everything else. But it didn't quite work as well as we would like. And you can get a better handle on this, not that much a better handle on this, by calling the pairs function, which it can take a vector of parameters and also some condition. So what this is supposed to do, and it actually did do, below the diagonal, it plots the two-dimensional density for all the transitions that didn't have Hamiltonian divergence, and above the diagonal, it has the iterations where there was Hamiltonian divergence. And if this came out better, you'd be able to see what is it about the draws of tau and sigma that are associated with a high probability of diverging. Unfortunately, the scale of the log posterior distribution is out in the millions, and so you actually can't see this too good. But I'll just tell you that we seem to see more divergence when tau was at the posterior mode, which is basically, again, reflecting this whole mode is too steep for Stan to deal with so well. So we're kind of running out of time. I want to show you briefly that you can get the indivergent and all that with this function called get sampler parameters. It returns a list with number of elements equal to the number of chains. I'm just going to bind those into a whole matrix. And you can see in the post warm-up period, so this is for the reparameterized one. It's actually not as bad as it might have looked on the plot. There's only like 2.5% are diverging, but because there's 8 chains, it looks like, each of them has a 2.5% chance of diverging. And you see a lot of rug marks in the post warm-up period. But you can also see some other stuff, like the mean acceptance probability got up close to 0.9 when its target was 0.8. And so that's not such a good sign. You see some tree depth things. sometimes hitting the maximum. So it got out into the tail and it took a whole lot of steps and it hit the maximum tree depth. That's not good. So some signs that things didn't go particularly well. And then one thing that could have been done, which we won't do, is to increase the target acceptance probability from its 0.8 default to something much a little bit bigger. And that will tend to make Stan take smaller steps, which will slow the whole thing down, but maybe it won't diverge when it's toward the mode. Another thing that could be done is to use the prior that we talked about on Tuesday that's based on the implication from the LKJ prior. So I'm just going to load that up without going through the code, although the code's in the zip file and we talked about it a little bit on Tuesday, even though we were sort of running out of time. Come on, load. Load faster. This is really big because it had to get it like 75 by 75 L matrix that it was also drawing from that ultimately we don't really care about. Come on. It only took like 5 minutes per chain to draw, but it has a lot of parameters to draw. Come on. So while that's loading, you can in the RStan demo package, there's like 125 examples that you can just call by their name. So you can see which ones have, good performance and which ones don't, and which ones need to be reparameterized and all this sort of stuff. If you call the Stan demo with just no arguments, it'll give you a menu that you can choose. And if you call it with the number 0, it'll give you the names of all 125 examples. But here are 8 examples from bugs that I
nine if you include camel 2.
9 if you include camel 2 that I remember as being what? Illustrative of some point. And so these all run pretty quickly, and you can source in the dependence function and the convergence function to see how Stan is performing with those. You can also look at the Stan code either in Shiny Stan or with the function get Stan code to see how those were parameterized or misparameterized. Come on. All right. Do I already have it in this one? Yes, I think I do. So this won't be on YouTube, but trust me, this is awesome. So depend. And then LKJ. I'll make I think just doing it twice made it not have enough memory. Okay, so I'm gonna not gonna restart. No. All right, crash. Perfect. All right. On that note, that's the end for this week. I will stop video. Stop broadcast.